Hi, my name is Johan Rodin and welcome to this presentation, Bring Your Engineering Course Alive with Wolfram SystemModeler. This presentation will describe some ways SystemModeler can be used in engineering courses. Let's take some time to think about why you'd want to use SystemModeler in the classroom. The first benefit is the sheer amount of material that can be processed with SystemModeler as compared to traditional manual calculations. This improves intuition and builds confidence in understanding of the material. SystemModeler is multi-domain, meaning that it's possible to combine different domains such as mechanical, electrical and thermal into one model. Models created with SystemModeler have an acausal structure, making it easy to see real-world reassemblance. There's also been a continuously strong demand for engineers with modeling and simulation skills. Since SystemModeler connects to Mathematica and the Wolfram language, a whole slew of new possibilities open up for analysis and design tasks, making it possible to evaluate performance of mechanisms and rapid access to a large variety of design tools. So where can you use SystemModeler? It turns out that it's in most engineering courses. Electrical engineering, mechanical engineering, aerospace engineering, industrial engineering, and so on. This presentation is example driven and we'll go through the following 4 examples: an operational amplifier and filter, mass and spring damper, control systems, robotics, and finally a short look at the Magnus Effect and user input. In the first example, we'll do live modeling of an operational amplifier and expand on this circuit. And we'll start from a clean slate here. So all the components that we need can be found in Modelica Electrical. And first off, we'll start by finding a ideal operational amplifier. So I'll take that guy and drag it out to the diagram view. We'll need 2 resistors, and these can be found in the basic components. So I'll select one of them, drag it out, and then duplicate it. We'll call one of them R1 and the second one R2. Notice that all these components are defined by equations, and I can open up and see what the equations behind them are. So in this case, V should always be equal to the resistance times the current I. I can connect this operational amplifier output to the resistors and also create an output point. So that's out there. Now I'll need to drive this with something, and we can find sources in the analog library here too. So I'll open sources and find the sine source. So there we go, sine voltage, and we'll connect it to the input pin there. We'll set this to be an amplitude of 1 and the frequency will be 1. Let's connect that to the resistor, and now we're almost done. Now we only need a ground component. So I'll find a ground component in basic, ground, and connect that to the sine voltage. Can now check that we have equal number of equations and variables, so the model is balanced and we should be able to simulate it. In Mathematica, I will now simulate this circuit by running WSM simulate and save the result into sim amplifier. We can plot the results with WSM plot, and we can see that we get an amplification here from the input to the output. If we change the values for these resistors, let's put a 3 for the R2 and 1 for R1 and rerun the simulation, we can see how that changes the output and we get a larger amplification for the output voltage there. Now we can analyze this data further by doing a data analysis of it. So we'll collect all the data into data, and then we'll use the Mathematica command find peaks to find the highest peaks in the data. So we'll find peaks at 26 seconds, 126, and so on. Let's plot that, and we can see here that where the highest peaks occur, and it manages to do this accurately. Now, to experiment with the model, I'll connect something so that we can run a real-time simulation and change. So what should we change? Let's change the resistance here. Let's make this into a potentiometer. So what I'll do then is I will click on change type here, and from the left hand side I will drag in a variable resistor. So we got that variable resistor there, and we can now connect this to the outside world with a connector. Like so. We can now start a real-time simulation, and we'll set up a control signal. So this will be what we send into this potentiometer. This will be the resistance in the variable resistor. We'll set this up so that when I change here, it will change in the model and the simulation. And we can now start this simulation. So we start the simulation, and as I change the resistance here, we'll see that the amplification gets larger and larger. So the green line is the resistance and the yellow line is the output voltage. Let's stop that simulation and add some complexity to our circuit. So we've managed to build a circuit that does what we want, but maybe we're interested in having a higher fidelity circuit. Maybe there is some saturation in this operational amplifier. So we'll do the same thing as we just did. We'll change the type of the operational amplifier and select one that has saturation. So we can find one of those in ideal components and OpAmp limited. So this one will have that saturation. So we'll now have a higher fidelity model. This one needs the saturation voltage here, so we'll add a constant voltage. I know that it's called constant voltage, so I'll search for it and drop that into place. Connect them to ground and set both of them together to be 5 volts. So it will saturate at plus and minus 5 volts. Good. Now we can do the same simulation as we did before. Where we have a gauge. We set that as an input and we'll do a real-time plot. So now when I run the simulation, we'll see that the amplification will still be there. It will work just like we did before. But when the voltage, the output voltage, exceeds 5 volts, we will see that it starts to saturate and keep it within those limits there, even when we go higher with the resistors here in the amplification. And when we come back down, we see that it closes in nicely there too. I should also mention that we can linearize the circuit. As an example, we have a low-pass filter here. If I open that in SystemModeler, we have now an input and an output, and we'll ask Mathematica to run a linearization and keep some of the parameters here, R1, R2, C1 and so on, symbolic. So what we'll get back is a state space model, and it will have those parameters that I asked for in a symbolic form. I can also say that I want the transfer function of this state space model and get that back between the input and output voltage. So to summarize, it's very easy to construct models. It's also easy to change the models and add complexity, and it's easy to interact with them in a virtual lab setting. Let's continue with a mechanical engineering example. This mass spring and damper model is a traditional model usually studied in a dynamics class. We want to know what is the position of the mass as a function of time. The traditional approach is to set this up using equations, use laws and theorems, and derive differential equations and then solve those differential equations. In SystemModeler, what you can do is encapsulate the knowledge that you have of how the spring and damper works into components, and then let the student compose the system and use the system. So, if we study the same system as we just had here with the mass spring and damper, we can construct this as a 3D model and run a simulation of it. Just as we did for the circuit, we can query all the variables in the system. So let's look at the displacement of the body here in the y direction. So you can see that it starts up at minus 2 meters and then falls down to minus 0.55 and then keeps on oscillating here until it finds a steady state. For 3D models, we can also see an animation of the system. We can see how that moves through time. So we're able to do the same thing, find the position, and we also get an extra insight by seeing the animation. But in SystemModeler we can take this even further. So let's do that by adding a force to this system. We'll add this to the body here, and it requires 3 inputs for the X, Y, and Z direction. So let's create 3 ramps and connect them to the world force. And let's have them start after about 4 seconds when we've reached the steady state time there. And we'll change the scaling here for the force arrow that will be shown. So in X direction, let's make the height a little bit higher. Let's do it 4, and in the Y direction, let's make the height minus 4. And let's do all of these for 5 seconds. Okay, so now when we simulate this again, not only will we be able to see the first steady state behavior, but then also what happens when we add the force. So there we have the steady state, and now we can see the force arrow here pushing this thing down and to the side. And if we want to see where it is, we can add a trace for it, so we can see that it starts up here, and then what's happening when we push that to the side. So what we learned here is that we can start from a small system, we can add additional complexity to the system, which would be very hard for the traditional approach here, where we would have to redo a lot of our calculations. And we can gain some extra analysis benefits by seeing this full system in 3D and see how forces react on it. In our third example, we'll look at how we can use control systems and robotics. So what we will do here is use components in SystemModeler, such as a revolute joint together with a body to form an inverted pendulum. We will apply a torque to this joint and then read out the value of the angle here and see if we can balance that upright. So what we will do here is use WSM linearize to find a linearized version of this pendulum that we've constructed. So it will take the input here and find a state space that transforms this input to an output. So in the state space model we have the input, the output, and the state variables being the angle and the angular velocity. We can now write this as a transfer function. So to do that, I call transfer function model on the linearized model that we have. Then we're going to assume that we're going to use a PID controller structure. So I create another transfer function, which we'll call PID TF. Now we can connect the controller and the plant, and we use systems model feedback connect to do that. So we get this full system here. Then we can use the built-in control theory, for instance PID tune, to find parameters. So here's 3 parameters for the K, TI, and TD values. And I've saved this into parse and parse vals, which we will now use. So we'll do a simulation of the system for 10 seconds, and we'll use WSM parameter values to use the values that we just found. So we run that simulation, and we can now plot the result and see here's the angle sensor that we use, and we can see that it reaches this desired level here after just 0.2 seconds, which is the upright position. We can now watch an animation of this inside Simulation Center. So I'll do that, and we can see in the animation, we'll slow this down, and we can see how it finds that upright position very fast. So the main points here is models can have more than one use. They can be used to understand something, and they can also be used to design controllers and verify that these controllers work as we want them to. SystemModeler, together with the Wolfram language, brings a full suite of capabilities for optimization, control theory, signal processing, and many other areas. In the last example, we'll look at the Magnus Effect in user input. Here we'll simulate the corner kick where the user supplies the force and the angle of the kick with the gamepad. In the animation we can see on the blue line being the velocity, the red the Magnus force, and the green the drag force. To calculate the Magnus effect, you'll need to know the density of the ball, the spin velocity, and then you can use a lift coefficient. Here we've approximated the lift coefficient from measured values. We've then used this in a multi-body model where the object, in this case a ball, has the drag attached to it, the drag force, and the Magnus force. We can then simulate this in parallel for a large number of different forces and angles of the corner kick. So if we run this for 300 different values, we can see that 45 of them, marked in green here, will hit the goal and the rest will miss. So the main points here is that it can be fun to interact with models. They can be connected to user input, in this case a gamepad, and you can use the Wolfram language for running massive parallel simulations. If you want to learn more about how you can use SystemModeler in education, there's a number of resources available for you. Inside SystemModeler we have a book about the Modelica language called the Modelica by Example. There's also a library for connecting Arduino boards to SystemModeler called ModelPlug. That's freely available from our website. And there's more than 50 examples on the SystemModeler website, where you can find free training videos, more courses, and also there's a community group for SystemModeler. Thank you for listening.